wizard. Now within your model wizard, you can choose what dimension you want to work in. For our analysis, we'll just choose 2D because that's much more easier. So, okay. So then you'll open to the select physics page. So here, depending upon the type of simulation you are working with, you can select the physics. So as Comsol is a multi-physics software, you can select more than one physics and it automatically will include like a coupler. That's automatic with the software, you don't have to add it. But for us, for today, so also, yeah, before I jump into it, you also have a beam module, but we don't have it in the basic license. So beam module will do something exactly what MATLAB does. It will replicate that. That is, you have like a line element and you give a thickness to it. Like basically a cross-sectional area to it, whether it be rectangular or circular. So for today, we'll just be doing a basic analysis. So don't ask questions, please sit down and watch.
You can sit there.
So next, so once we add the physics, it comes in the added physics interface. It's important for it to be here, otherwise you can't proceed. So then you can immediately go to the study button. Nida. So you can go to the study button. Once you click the study button, you will have stationary. So here you have, please don't talk when I'm bringing it. So you have these studies. You can choose either the eigenfrequency analysis, stationary or time dependent. So for today, we're just doing a stationary analysis. So there is no need for the other two. So we click here, done. And once we do this, the physics and the study is added into the interface. So you will notice it here. So I'll just close this. In the model builder, you have the study included here. I think I'll make it a little bigger, right? Because it may be a little difficult for some. Just give me a second. I'll make the screen slightly bigger.
You can go to full screen.
Oh, what do you say? Go to full screen mode?
What do you have to work on?
Okay.
Like on the right side, you can see the arrow, right?
Huh?
On the right side.
There's an
Right end.
frequency. Which one you have to?
No, the right end arrow.
Time dependent of
Right
this.
end.
Oh, you mean
Ah.
here? Huh?
You're sure?
Click that.
Yeah, full screen.
Okay.
We have to be stationary.
Yash, these one, I'll answer your questions. Please watch carefully. I'm telling it in detail, right? Please come and sit here. Yash, it'll be much easier for you to see. I think your laptop has been charged sufficiently enough. Okay, that's going to make a lot of noise. If you can bear the heat for it, bear the heat. Yeah, so now once you enter into the model builder, you see there are a few options here. You have geometry here. Wait, none of you have eyesight issues. You can now see what I'm doing, right? All of you can hopefully see. So geometry, then you have materials, then you have the added physics here. So whenever you add other physics, you just keep, so it's basically like how you write a code, right? There is a function hierarchy. So here, solid mechanics was added first, solid mechanics will appear first. So now if you add another module, which is a combined, there are combined modules, like say that you put heat transfer in solids and few others like Joule's heating. So Joule's heating is a coupled physics where automatically you'll get 3-4 modules. So they'll come in an order. So this is where you'll have the physics falling in order. And after that you'll have your mesh. That is where you'll mesh it depending upon the type of custom mesh you want. And finally, because we added the study as well earlier, we have the study here. But let's say we didn't add that, we directly opened it by skipping the select physics and the study edition. You can always come here on the top. Let me just close this. Oops, that is the full screen. Okay. Yeah, so you can always come on top, and here you have the options to add so you can add the physics from here too, and you can add the study from here too. So you don't, if in case you skip it earlier, you can always add it over here. Now for your problem in particular, we are going to just be trying to create first a line to define the shape of your truss, and then orient beams along those lines. Because as I told you, the CAD interface here is not like a usual CAD interface where you can pull a line and draw. You'll have to define it by coordinates, and for a rectangle, you have to define it by rotations and also coordinates again. So what I'll start with is, I'll start with that I think in one of the examples Suresh had given. So we'll go to geometry. So one thing in Comsol which is good is you can express parameters earlier ahead. So I'm going to do this. I'll just do a simple 3D model first. So we'll say A1 is the, okay, we're not, so I'm doing one thing here. Because we're using 2D, we have an out of plane thickness which will associate common to everything. Each cannot have this different out of plane thicknesses. So in order to accommodate this area of cross section, I will be using the dimension in plane as the variable and keeping the out of plane constant. So that the out of plane is 1. The in plane thickness will be the area of cross section. So basically then B into T will be A, right? So I'll be using that. So I'll write it rather than B so it will not be confusing. So B1, I'll take a number here, let's say 0.06, and now you in the parameters you can explicitly define a unit by putting square brackets and writing like meters. So when I click enter, it will now be defined as meter. If you don't explicitly define the unit, it's just it's like non-dimensioned, and so when you use it in the GUI, it will take whatever dimension is associated with that line, which I'll show you ahead. So then we'll take a similar width for breadth for all of them. So okay, this is B2. So we'll take this also to be around like say 0.3. So now once we have defined this, we have the variables to work with. So we can directly now jump into, open up the component, go to geometry, right click geometry, and under geometry we have rectangle. So we will click rectangle. Now as you see, the rectangle they have a size and shape associated with, that is just the width and height. Then you have a position control. So here you have two types of control, a corner control, a center control. A center control will be the center of the body will be associated with the position. Corner is the right corner will be associated with the position. So I'll be using the corner control, and then finally you have an overall rotation.
There is no rectangle.
Don't let this follow. Yeah. So now with the width, I had defined earlier a particular width, right? So I'm going to change it slightly here. Just you can do it how you want. You can either put that B1 for height or width. The only thing all you'll be changing is your rotation. So it doesn't matter where you put the value. So I'll use this as my length. So let's say I'm going to have a structure. So just draw it. We'll take a structure like this. We'll keep this as the fixed point. We'll keep this as a roller, and then we'll add a load here, right? So this point, which I'll be taking this as -2, 0.65, this as 0, 0, and this as 0.5, 1.5, because this is close to one of Suresh's examples. So the load here I'll be putting is 1,000. Yeah, so that's what I'll be putting. So we'll define the width. I'll just put some value. Let's say I'll put 1.6 for now. So keep in mind the units is meters. Then the height, I'll give you a B1. So now when I go on top, build selected and build object, all objects are there. Build all objects will ignore a hierarchy and will just build everything from the start to finish. Build selected will build every object up to the current object. So anything previous to it, it will not build anything post to it. So when I click now build selected, you'll have your first beam here. But now we want this beam, so also let me put an element number to it. So we'll take this as 1, 2, and 3, right? So we'll follow this. So I want this now rotated, right? So in order to rotate this, if I don't have a reference, it's going to be very tedious. So for that, what I'll do is I'll initially use a line element. So I'll go back here. We have a line segment. So now I'll go to coordinates. So 0, 0. Now I'll define the next coordinate. So that is -2 and 0.65. So if I click build, select it, and now I'll click this icon here, which will be like a fit to page. Now you see that's the line I want this beam to go along. So that line has nothing to do in the FE. It's just a construct for me to move something to. Because otherwise I won't know the rotation angle to give. It's like a trial and error. Unless you hand write it out, calculate the respective angles, which I have not done. Right? So what I'll go back to the rectangle now. And now I can rotate it. So I'll rotate it here, let's say 170 degrees. Okay, that's a bit too much. So let's say 165. Okay, that is also still large. Yeah, so maybe around 162 maybe the value. So you can keep tuning it to get it along that. Then I'll change the width. So don't worry about width and height as I told earlier. These are just basically like a length and breadth term. So I'll change this a little more. I'll make this like maybe 1.8 to, okay, so that's still a lot more. So maybe it'll be say 2, because it's -2, right? So it'll be more than that. So it'll be 2.1. Yep. Right, so that's the first beam which we finished. So now I can go ahead here and disable this line segment, because we don't want this involved, because the mesh will have an issue if you have a line segment in between. So I'll disable it. So we have rectangle 1 done. Now we'll move to the next. So here I'll just start with the line segment first. So again, go back to coordinates. Could you close the door if you don't mind? The light might hit the screen. So now the next is between -2 and 0.65 to 0.5 and 1.5, right? So that's your next element. So now when I use a rectangle, I'll have to also use, okay, so I can duplicate it. So the one easy way is, once you get good at this, you don't always have to keep going at geometry. You can just right click a rectangle and click duplicate, and you can keep just adding sequentially, but for now I'll just do it the hard way. So so the next rectangle will be B2, and let's put a width of, so this will be around, maybe let's start with something like 2.5. You can always reduce it. No, I made a mistake. I put commas. Okay, now I need this corner to go all the way there to the other end, right? So first what I'll do is I'll adjust this position. So this is where I tell you Comsol is tedious in all of this, right? So we have to move to now -2 and 0.65. Now we've gone to that corner, right? Now we again have to apply a rotation. So this probably looks like, I do not know, maybe let's try 50. Okay, that's too much. So it would have been much less. Let's say 28. Still more. So 15. Okay, so it's like 17. Okay, so now because it's a very small game, maybe 17.5 would. Okay, so it's still a little larger. So this is where I told the one with the most number of beams, I wish you all the best. If you are smart, you can do this through code, but that is, I do not know if you want to put that much amount of effort into. Okay, this is so now you understand the tuning you'll have to keep doing to get it. Yep, so approximately there. So the exact thing may be 8.5, around 8.5 to get it adjusted. So now I'll increase the length a little bit more, maybe 2.6. Okay, 2.7. So we don't have to worry about it extending beyond, and you'll know why. Okay, so okay. Next is the next element. So we'll again go there. We'll add the line segment. So here the line segment, we have to put it in coordinates. So while we do that, we go and disable the previous one so we don't have that remaining. So I'm not showing you the efficient way of doing it. The most efficient way is create all the line segments and do the rectangles, because you can just sequentially duplicate. So that's the fastest. Or you can use a vertex method to connect the points. I'm just showing the tedious method. So see, so now we have to move from 0.5, 1.5 to 0, 0. Right? So now again we create a rectangle. So here we have B3. And this B3 is just to show you about parameters. You can directly go ahead and put your value there. This is just to show you that you can use parameters for your future studies. So the width here, you can put maybe like 1.5 just to start with. So build all of this. So now I'll apply a rotation. Let's try 70. So maybe around 72, maybe I think a bit too much. Oh, actually around right. So okay, so it's very close to 72. Okay. Let's get it as close as we can. Yeah, okay. So that's around, that's very close. So extend this beyond. Right, now the problem what happens is if this connection is not being made continuous, right, it will just separate. So I'm going to now move this position a little lower. So you can either use the move function and give a displacement vector, or the easiest is just to continue using position and play with it. That is, just keep moving it and moving it back. So here I'll just move it a little to the left and little down. So maybe minus 0.1. And here I make
Actually, I'm waiting.
yes afterward. And minus 0. Let's say 2. Okay, this is too much. So maybe put a 0 1 there. So basically, I just wanted to intersect. So if it intersects, I can remove those edges and get it as a continuous value. Sorry. Yeah, you can see it just about intersects there. So now I can remove that edge. I can remove this edge. So once we do this, let's intersect these two as well. These two beams, right? Let's make them intersect as well. So I'll go back to the previous rectangle. 2.7. I'll make it. Okay, I'll go back all the way to the first one to increase that length first. So we'll make this 2.2. And now we'll make the next one a little lower. So now I'm going to control the position of this. So I have to enable the previous line segment just to have a reference. Build all. So now I have that line segment there. I'm going to just move the second element a little bit. So we're going to go okay minus 2.01. And here we go, let's say 6, 3. So now it's still not intersect. So let's go to 6. Yeah. Now we'll just move it up a little bit. So actually the preferable is for the line to be along the center of the beams. So you all can take a little more effort and place the line along the center of the beam. That is like a neutral axis. So you have to play with that, but it's just going to be honestly tedious. I'm not going to do that now.
Line along the center.
The line segment which I'm drawing as a reference, right? Preferably let it be at the center of this rectangle. Center means that it will be the partitioning line,
yes,
right? So it divides it into two halves, neutral line.
But what I'm not getting is how we'll connect these two.
Don't worry about that. Is what I'll show you now. Right. So I will just move this a little bit more. Just hold your question, please. Yeah. So now it looks like a lot of them are intersecting fine. So we can go now to the geometry, right click it, go to virtual operations and ignore edges. You click the ignore edges option. Now I'll disable this line segment which was previously created, both of them. So disable. Disable. Now in ignore edges, I will use the zoom tool and zoom each of these connections. Right? So if I click build all, it should remove that line. Okay, don't worry about this. So I now edges. So first you activate the selection. That's that left icon. It becomes green. Then you can start selecting the element edges you want to remove from the connection. So say I want to remove these edges from the connection. Anything which is within the gray region can be removed. So we go here. So I want to remove this. So now if I click build all, you see that gets removed. So if you perfect your arrangement, you will not have these little bumps here. So your mesh, because we'll be using adaptive mesh technique, you'll get a little fine mesh around here because of this notch. So now if you look at the structure, you have the connections made without these intersections. So you won't have too much of adaptive meshing at the connections now because there are no more intersecting lines. But you'll definitely have it at the corners. So once we are done with this, so the form union will automatically be established. You don't have to go build it again. We create a material. So right click, we create a blank material. So now it automatically opens this. So let's give something like
79.
1E9.
79. It's okay.
Yes, please keep it. Then density will give it around 1600, right? So now, once it's been established, all these properties are now given to the domain. Then we come to solid mechanics. Now you click solid mechanics, you see the type of model you're using here. So we are using a plane strain model. And here is where that out of plane thickness comes. So I've kept this as 1. So now if you multiply this with your B1, B2, you get your area of cross section. That's simple. Right? Now I right click solid mechanics. Now here we have the boundary conditions you want to give, the fixed constraint. You can use a roller, I just prefer using prescribed displacement. And then you have the boundary load. So all three required. Now let's say you want to give it at a point. So these are for bound. So for 2D, a boundary means an edge and a point meets that vertex. And in 3D, a boundary means a face and then a point will still hold its same context in 3D. So that's a small difference between 2D and 3D when you move. So for now, we're giving it on a boundary. So I will take the fixed constraint first. And on that, say, I'll just apply it here. So I want that to be fixed. Next, I will go to the prescribed displacement. And I want a roller to be here. So just constraint Y. And the last is the load. So the boundary load. So now we want it as total force, not as force per unit area. So total force, and then we'll select, let's say, this region here. So now it's 1000 in both the direction. So we'll give you 1000. We'll give you 1000. So once we do this, the boundary conditions are done. So you can go ahead and close this. So now the outer plane thickness is given as 1 meter. Now we come to the mesh. So generally people love using a physics control mesh because that's the easiest thing to do. But I don't recommend people to use physics control mesh. They really can't control, in some sense, partitioning strategies from using a physics control mesh. So what I'll do is I'll just jump to user control because it's much more efficient, and for the further use of Comsol ahead in this course, you will be using a user control mesh. So we'll go to user control mesh. We'll be basically using these constant strain elements, which are tri-elements. Also, they are also known as free triangular here. So now here we go to the size option. sizes, what's the size of the given element, and we'll give a minimum maximum size associated with the element. So I presume all of you know what FE elements are, right? In some sense, there's no need for explanation in any context. So we go to custom. So now I want my maximum element size to be restricted to a value which is reasonable within this given thickness. So because we took 0.06 as a minimum dimension, and here I told you, right, it's explicitly enforced in meters. So this is what I said will happen if you don't put a unit in the start. So if I put mm in the start, right, it will override this meter here. So if mm was explicitly defined in parameters, it will override the GUI's unit here. So that is something you have to keep an eye on Comsol. So now over here I'll put, let's say 0, 1, and I'll say build order. Now you have it pretty dense, the mesh. Right? Don't worry about it. It's a linear analysis using a direct solver. Your mesh density is not a big deal here. It'll solve within seconds. Then we come to study. So now in study you don't have to change anything here because you're not using any geometric nonlinearity. The basic license doesn't have it. So all you have to go do is just click this little button here, compute. That's it. So now what you get is like similar to MATLAB. You'll have some cubic interpolation of the deformation. Then you can come here to stress. You see results. You see stress here. Drop down on stress. You have surface. It's a surface plot. Drop down on surface. You have the deformation scaling. So you notice it's been scaled by like 1,256. So you can just reduce this if you want. When you're doing other simulations, you want things to be a little more representative. If you want to put, you don't want to show it like as if it's buckling, right? So you can just reduce the scale factor. Now you see something more realistic to what you get in MATLAB, right? So once this is done, now you want to know the strain energy. So now you see the stress is almost distributed along the length of the Now we will go and plot the total strain energy because that's what you want to see at the end. So we go to this little icon here. So click surface first, then go to this little green and red icon, drop down on it, go to solid mechanics. Now solid mechanics, you notice there's a continuation between what we added as a physics and here. Then go to global, we want the overall strain energy. So we go to total elastic strain energy. We double click it, it enters the expression here with its unit. And all you got to do is plot. So here in this case of all the values I've taken, it's 0.05, right? Now what is interesting to try is, this is in a way not considering the element as a truss. So it's also including bending. So now for bending, we know that cross section matters, right? If I change the cross section, I changes, and bending automatically, the stiffness of the structure will change. Because if I changes, bending is obviously restricted, right? So for that, you can also try by taking the square root of your area of cross section, then give that value, because here I've taken everything to be the same, right? You can give one of that values to this, and the other value you can come here and give it here. So basically it's a square section. Then you can see how much does your strain energy change.
Just a quick question I wanted to ask. That part I got, but in so we will have to add that to the system inside. I mean, like B1, B2, B3, we will have to add the square root. Okay.
No. You can define the cross section how you want it to be. I'm just telling if you want to verify that bending is not dominating, right? That is, you have a bending included here, right? Unlike a truss extension compression, you have here bending. So for bending, I plays a role. That is your second moment of area.
Yes, of course.
Yeah. So you want to test that if I change the cross section, that is out of plane. If I change the out of plane dimension and the in plane dimension, what change?
Okay.
Okay. Let's hold the other questions. Let me just finish this. Now, once you try this, you can always go back here and just try a mesh convergence. So I took a very fine mesh, but if you start with a coarse mesh, you can proceed with a mesh convergence. Now, there are other ways to play around with this. Is make sure that your load is as axial on all the elements as I told you, instead of having it highly transverse. So you reduce the bending dominance in some sense. You get that is, you're putting the component of load as much along the axis of both the beams. So if you have a complicated structure, all the best again. But this is the way you at least initially approach it. Now I'll show you a few other features also which can be used. So let's take a step away from this. So this is what you'll have to do. This is what Suresh wants you to do. Now we'll also see how we can probe in Comsol. Probe is I want to take out values from here. So if I'm giving a load, I want to take out a displacement. So what I'll go to definitions. So let's say we're giving a load at that tip. I want to take the displacement from that tip. So we'll go to definitions. I'll right click definitions and we have something called probes here. So I'll take a boundary probe. So you can go to a boundary probe. So then immediately clear the selection. It will default select everything. And I'll go to the boundary where I gave that load over here. Right? So I'll have to click that. Now once that's selected, I want the average of the values of displacements there. So now this will be the magnitude. You can also give u, v, w and take the components. So now if I run it again, keeping this probe, you will get in your table, you will get the corresponding displacement value there. Displacement magnitude. So this way, even if you're doing a displacement control and want 4 reaction force, the same process is involved. Probe it, ask for the reaction force, give the displacement, and you'll get the corresponding force. Right? So this is what you'll have to do. So y'all can start trying it. This is just the introduction part of it. So hopefully this shouldn't be too difficult. And if you want to plot graphs or anything for these in terms of let's say strain energy stress, you can just export them from here and take them out. Alright, so for those who have the files I've installed, go ahead and try to set it up. I'll help you, and then you can start doing your assignment, and any doubts I'll help you out. Yeah, everybody got the picture?
Yes.
Okay. You got the picture?